Hello, and welcome to this online lecture. My name is Patty Kokish, and today we're going to be going through topics for your online Math 200 class at Ivy Tech. So today, what we're going to cover is Chapter 6, which is all about discrete probability distribution. Discrete probability distributions. So we're going to start with section 6.1, which is about discrete random variables. So the objectives in this section include being able to distinguish between discrete and continuous random variables, identify a discrete probability distribution, construct probability histograms, compute and interpret the mean of a discrete random variable, interpret the mean of a discrete random variable as an expected value, and finally, compute the standard deviation of a discrete random variable. So for objective 1, we want to learn how to distinguish between discrete and continuous random variables. So we've learned about discrete and continuous before, so this shouldn't be too difficult. But first we want to define what a random variable is. So a random variable is a numerical measure of the outcome from a probability experiment, so its value is determined by chance. Random variables are normally denoted using letters such as the capital letter X. So let's look at this example here. Suppose we flip a coin 2 times. The outcomes of the experiment are either going to be heads and then heads, heads and then tails, tails and then heads, or tails and then tails. So rather than being interested in a particular outcome, we might be interested, for example, in the number of heads that we obtain when flipping 2 coins. Since the outcome is numeric, meaning we either get 0, 1, or 2 heads, the outcome is called a random variable. So a discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with spaces between each point. So this is the same thing when we talked about discrete measures before, we can count them. A continuous random variable has infinitely many values. So if you're going to plot them on a number line, you have to shade through the entire number line in an uninterrupted fashion. So it includes decimals, fractions, that sort of thing, any real number. So the first thing we want to do is determine whether the following random variables are discrete or continuous, and then state the possible values for the random variable. So the first thing is the number of light bulbs that burn out in a room of 10 light bulbs in the next year. So if you think about this, we could count the number of light bulbs that burn out. So that's going to be discrete. It's going to be somewhere between 0 and 10 because there are going to be 10 light bulbs in the room. The number of leaves on a randomly selected oak tree. Again, we can count these. We don't really have an upper bound that we can put though. Like for the last one, we could put 0 to 10 because we knew there were going to be 10 light bulbs in the room. This one, we can't really put any upper bound because we don't know the maximum number of leaves. And the length of time between calls to 911, this is going to be continuous, where time is greater than 0, meaning it couldn't really take on any number from 0 all the way up to probably, I don't know, that we don't really have an upper bound. My guess is, there is some kind of upper bound since 911 is constantly receiving calls, but we can't really put one on there because we don't know what that is. But it can take on any values in that range, not just whole numbers. Okay, objective 2 is being able to identify discrete probability distributions. So a probability distribution provides the possible values of the random variable x and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or a mathematical formula. So if we look at this right here, the table to the right shows the probability distribution for the random variable x, where x represents the number of movies streamed on Netflix each month. So we have values 0, 1, 2, 3, 4, and 5, and we have probabilities of 0.06 or 6%, 0.58 or 58%, 0.22, 0.10, 0.03, and 0.01. So if you recall, the rules for probability distributions, they're the same as they were before. The sum of all of the probabilities has to equal 1. Okay, this symbol right here is a summation. So summation of all the probabilities is equal to 1, and all of the individual probabilities have to be somewhere between 0 and 1, where 0 would be impossible and 1 would be certain. So if we look at this was our previous example. This one, if we add this up, we get 0.97, so that means that this is not a probability distribution. All of the individual probabilities are fine, they're all between 0 and 1, but when we add all these up, we do not get 1, so it is not a probability distribution. Okay, now they just changed one number, and if you notice here, they changed it to a negative number, so we want to know if this is a probability distribution now. We cannot have negative probabilities. We're always going to have probabilities somewhere between 0 and 1, or meaning 0 and 100%. So we can't have a negative probability. So this one is not a probability distribution either. But finally, if we change this number to 0.04, I think now if you add all of these up, you do get 1. And if you look at all of the individual probabilities, they're all between 0 and 1. So that means that this is a probability distribution. Okay, objective 3 is to be able to construct probability histograms. So a probability histogram is just a histogram in which the horizontal axis corresponds to the value of the random variable, and the vertical axis is going to represent the probability of that value for your random variable. So this is very similar to how we constructed histograms previously. So if we want to draw a probability histogram of the probability distribution to the right, which represents the number of movies streamed on Netflix each month, what we would do is we'd put our values 0 through 5 along the bottom, and we'd label them number of movies streamed. We have a chart title as well, movies streamed from Netflix. And then along the side, we put the probabilities. You could either have them as decimals or percentages. I think either would be fine. And then you just plot it as far as it goes. So for example, 0 movies is 0.06, so that's somewhere between 0 and 0.1. 1 is the highest bar, 0.58, so that's pretty close to the 0.6. So you can see we have just a probability histogram right here that represents the same data, except just a little more visually than a table. Okay, objective 4 is to be able to compute and interpret the mean of a discrete random variable. So the mean of a discrete random variable is given by the following formula. So we have mu of x, remember this is the Greek letter mu for mean, it's equal to the summation of all of the x's times their probabilities. Okay, so x is going to be the value of the random variable, p of x is going to be the probability, okay? So the mean is just going to be whatever you get when you multiply the corresponding random variable by its probability and then add it all up. So if we look at this example, compute the mean of the probability distribution to the right, which represents the number of DVDs a person rents from a video store during a single visit. So we have our x's and we have our probabilities. So what we want to do is we want to multiply the corresponding numbers and then add them all up. So for example, we take 0 times 0.06, 1 times 0.58, 2 times 0.22, 3 times 0.10, 4 times 0.03, and 5 times 0.01. And then we just add them all together because we have this summation symbol right here. And we get 1.49. So that's the average number of DVDs a person rents from a video store if this is the actual distribution. So about 1.5 videos. Now with these, you always want to ask yourself, does my answer make sense? So if you look, the biggest proportion of people is between 1 and 2. Okay, if we look at the number of videos here, we have 58% at 1 and 22% at 2. That means we should probably end up with a number somewhere between 1 and 2. Okay, and we got 1.49, which seems pretty reasonable. These are the types of things that you want to think about though. If, for example, you got an answer of 10, you know that that wouldn't make sense because all of the numbers are between 0 and 5. Okay, so you have to think about this logically and figure out, does my answer actually make sense? Is it in a reasonable range of values? And even furthermore, is it next to the ones that have the highest probabilities? Because that's kind of where it should be pulled. Okay, so if we want to interpret the mean of a discrete random variable, let's suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of the n trials will approach mu of x, which is the mean of the random variable. So in other words, we let x1 be the value of the random variable x after the first experiment. X2 is going to be the value of the random variable after the second experiment, and so on. Then the difference between x bar and mu of x gets closer and closer to 0 as n actually increases. So the following data represents the number of DVDs rented by 100 randomly selected customers in a single visit. We want to go ahead and compute the mean. So for this one, what we would do is we just add all of our observations up. So 1 plus 1 plus 1, all these ones, plus the 2s. And you'd keep going. You'd add it all up. Hopefully you'd use Excel or StatCrunch or Minitab. And then you divide by the number of numbers, which is 100. And we get 1.49. So if we look here, when we started, so when we had only maybe one trial, we had a person who rented one DVD, okay, and then another person who rented one DVD. And then we probably had an additional person that rented 2 DVDs. So then the mean was brought up to 1.5 and so on. So these first trials, these aren't very accurate. But if we start to look kind of further and further along this line, as we had more and more people renting DVDs, and as we started to actually count those, you'll notice that what happens is as this trial number increases, okay, so as this approaches infinity, or 100 in our case, it gets closer and closer to this line here. This line is a line that's at 1.49. That's our mean that we expect, okay? That's mu of x. And it's going to approach this value as we get larger and larger sample size. Okay, so if we want to compute and interpret the mean of a discrete random variable as an expected value, we basically can say that because the mean of a random variable represents what we would expect to happen in the long run, it's also called an expected value, which is normally denoted E of x, okay? And this is the expected value of the random variable. So let's look at this example here. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. According to the National Vital Statistics Report, the probability the female will survive the year is 0.99791. And what we would like to do is we'd like to compute the expected value of the policy. So all we have to do is use our same formula for our mean. So if you kind of create a table here, the possible outcomes are that the person either survives, okay, so the 49 female lives through the year, or doesn't, okay. Now, if she lives through the year, then the insurance company made $530. They just pocketed that $530, and then she gets nothing at all. Now, that has a very high likelihood of happening, 0.99791, because most likely she's going to survive. Now, the probability that she doesn't survive the year is going to be 1 minus whatever this was, okay? Because together, if you recall, these have to equal 1. So if we add them up, they have to be 1. So if you're missing one of them, what you have to do is take 1 minus that value. So in your calculator, if you do 1 minus 0.99791, you're going to get this value right here, 0.00209. And then in order to get the amount that the life insurance company is going to be kind of out, is going to be to take the $530 that she paid and then subtract the $250,000 payout that the insurance company would have to make upon her death. So the insurance company would lose, so you notice it's negative because they're losing money, $249,470. All right, so quite a bit of money, but there's not a very high likelihood of that happening. So if you recall, the way that we find the mean or expected value is to multiply the things that go together. So we take our x's and we multiply by our probabilities. So we take our 530 and we multiply by our 0.99791. And then we take our other x, which in this case is negative. Okay, so you're going to have negative 249,470 multiplied by the small probability because she doesn't have a very high likelihood of dying, 0.00209. And then you add those. Really, this turns into subtraction since this is negative, and you get $7.50. So there's no interpretation written here. But what this means is that in the long run, companies who sell $530 policies to 49-year-old females are going to make about $7.50 on each policy on average. Now, they can't actually make $7.50 on any one policy. They either make 530 or they lose 249,000. But in the long run, what we would expect to have happen if many of these policies are sold would be that on average, they make about $7.50 per policy. Okay, objective 6 is to be able to compute the standard deviation of a discrete random variable. So if you look here, we have our standard deviation going to be equal to, and then we have the square root, and we have two different formulas here. You take the summation of your x's minus the means and square them and multiply them by their probabilities, and then you add that all up, okay? And then you take square roots. Alternately, you could take x squared times the probability of x, add that all up, and subtract the mean squared, and then take the square root. X is going to be the value of the random variable, mu of x is going to be the mean of the random variable, and p of x is the probability. Now, either of these work just fine. I'm going to walk you through how to do this, but it would also be kind of important to note that StatCrunch will compute these values for you as well. So let's compute the variance and standard deviation of the following probability distribution, which again represents the number of DVDs a person rents from a video store. So if you recall, the mean for this problem was 1.49 when we found it. All right, we have all of our x's, we have all of our probabilities already, and we have our mean, which are kind of the three things that we need in order to get started. So if you look here, the easiest way to set it up if you're going to do this by hand would be to maybe set up some kind of chart, okay? So the first thing you're going to do is you're going to take your x values and you're going to subtract the means, okay? So for example, I'm going to take 0 minus 1.49, 1 minus 1.49, 2 minus 1.49, all the way down, okay? And then you take all of those values and you square them. Please recall that anytime you square a number, it should always be positive. So this entire column should always be positive. If you're not getting positive numbers when you're doing it in your calculator, it means that you're not putting parentheses around your number when you're squaring it. So if you want to do negative 1.49 squared, you have to put a parenthesis, then type the negative 1.49, end the parenthesis, and then hit your square button, and that will work. Okay, so we have all of these values. We have the probabilities as well, which were already given. And then we just multiply the x minus mu of x squared times the probability. So for example, we take our 2.2201 times our 0.06, and we get this value here, 0.133206. And we just do this all the way down. And then we add them all up. And if we add up this entire column, we get 0.8699. That's going to be our variance because we haven't taken the it's going to be our variance because we haven't taken the square root yet. But once we take the square root, then we have the standard deviation, which in this case is going to be 0.9327. Okay, section 6.2 is about the binomial probability distribution. So the objectives in this section are to determine whether a probability experiment is a binomial experiment, compute probabilities of a binomial experiment, compute the mean and the standard deviation of a binomial random variable, construct binomial probability histograms. So the first thing we want to talk about is the actual criteria for a binomial probability experiment. So if you want to determine if something's binomial, you have to first understand what binomial means. So an experiment is said to be binomial if the following are true. First is that the experiment is performed a fixed number of times. Each repetition is called a trial. The second thing is that the trials have to be independent. So that means that the outcome of one trial cannot affect the outcome of other trials. Third, for each trial, there are two mutually exclusive, or we could call them disjoint outcomes. It's either a success or a failure. And fourth, the probability of success is fixed for each trial of the experiment. So here are some notation things we're going to see, all right? There are going to be n independent trials in the experiment. P is going to be the probability of success, which means that 1 minus P is going to be the probability of failure. Now, if you recall, The reason for that is because we have two outcomes, either success or failure. And if you remember, probabilities have to always add up to 1, okay? So if the first one is p, then in order to get the other one, we just have to take 1 minus p. Okay, so p is going to denote the probability of success, 1 minus p is going to be failure. X is going to be a binomial random variable that denotes the number of successes in n independent trials. So for example, n is going to be our upper bound, okay, because that's going to be the number of trials. X is going to be the actual number of successes that we see. Okay, so which of the following are binomial experiments? So let's say we have something like this. A player rolls a pair of fair die 10 times. The number x of sevens rolled is recorded. So this is a binomial experiment. So if we look at it, we have 10 trials. Okay, so let me go back to our qualifications here. We have 10 trials. They're independent. If you roll a die once, it has nothing to do with the other one. We have a success or a failure. Okay, so for example, success would be getting a 7, failure would not. Okay, and then what was the last one? Oh, the probability is fixed for each. Yes, so the probability is going to be the same every time that you roll a fair die. Okay, let's look at this one. The largest 11 airlines had an on-time percentage of 84.7% in November of 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. The number of flights X that needs to be selected is recorded. So this is not a binomial experiment because it's not a fixed number of trials. So she just selects flights until she finds 10 that were not on time. So she could select 20 flights, 30 flights, 100 flights. We don't really know because she has to continue to select until she has 10 that were not on time. So because there's not a fixed number of trials, this is not a binomial experiment. Okay, in a class of 30 students, 55% are female. The instructor randomly selects 4 students, and the number X of females selected is recorded. So this is also not a binomial experiment because the trials are not independent. So if you think about it, if we have only 30 students in a class, if I select one of them, then that means that they've been picked out of the pool. Okay, so then when I go to select another, that person, or our probability changes of getting a female because we've already selected one of the females out of our 30 students. So every time I pick a new person out, I'm affecting the probability. So the trials are not actually independent. Okay, objective 2 is to actually compute probabilities of binomial experiments. So the binomial probability distribution function is as follows. The probability of obtaining X successes in n independent trials is given by the following. Probability of X is equal to, and we learned this notation last time, this is combination notation, okay? So NCX times the probability raised to the X power, this is the probability of success raised to the X power, times 1 minus the probability, which is the probability of failure, to the n minus x power. So x is the number of successes, so we raise the probability to that power, and then we raise the failure probability to the failure power. So here are a couple of phrases and the math symbols that go with them. These are important to understand. So if you see at least, no less than, greater than or equal to, you're going to use this greater than or equal to symbol here. More than or greater than is going to be just a greater than without the equal to part. Fewer than or less than is just going to be the symbol like this, where we have a less than sign. No more than, at most, or less than or equal to all mean the same thing, and they mean less than or equal to. And then exactly, equals, or is just indicates that you have an equal sign. Okay, so according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? So we want the probability of getting 5 successes. So we take 20C5, and then we multiply that by the probability of success, which is 0.35 to the 5th power, That's our number of successes. And then we take 1 minus 0.35, which is going to be our failure rate, to the number of failures, which is going to be 20 minus 5, or 15. And if we do this in our calculator, we get 0.1272. It's also important to note that you can look this up on a table. Okay, so there is a binomial table in the back of your textbook. And if you look on it, if you look at n equals 20, and you look for x equals 5, and you want an exact probability, so you have to make sure you're looking at the exact binomial table, you will get this value here of 0.1272. So all of those tables, I believe, are provided to you on the exams. You have to make sure that anything that you need like that is provided. So check with your instructor. But that should be provided to you. And at that point, you can just look it up on the table instead of having to calculate it by hand each time. Okay, same kind of setup, but in a random sample of 20 car-owning households, what is the probability that less than 4 have 3 or more cars? So that means that we want the probability that x is less than 4. Now, probability that x is less than 4 is equivalent to saying the probability that x is less than or equal to 3, okay? Because we don't want 4, we want 3 or less. So that means we'd have to find the probability of getting 0, 1, 2, or 3. So in this case, if you were doing it by hand, you'd have to do 4 separate calculations by hand, and then you would have to add them all together, which is fine. But if you use your binomial table in the back of your textbook, now what you want to do is you want to go to the cumulative table. Okay, so for the cumulative table, it gives you values that have already included basically for this less than or equal to. So if you find n equals 20, x equals 3, then that means it's already added 0, 1, 2, and 3 together for you. And you should be able to find this value of 0.0444 on your actual table. Okay, in a random sample of 20 car-owning households, what is the probability that at least 4 have 3 or more cars? So that means that we want to find the probability that x is greater than or equal to 4, okay? Now for this one, really, if you have x greater than or equal to 4, that's just the opposite of x less than or equal to 3. So what we can do is we can take 1, which is our total probability, and subtract the probability that x is less than or equal to 3. And we already found this probability before. We found it in the previous step. It was 0.0444. So we just have to do 1 minus that value, and we get 0.9556. So it's important to note that if you're looking up an exact probability, you need to be on your exact binomial table. If you're looking up a less than or equal to probability, then you need to look on your cumulative table. And if you need something other than less than or equal to, or just equal, then you need to figure out how to rewrite it so that it has less than or equal to in it. So for example, we took this greater than or equal to, and we rewrote it so that it had less than or equal to in part of the actual problem. So then we were able to use our table value in order to find that. Okay, objective 3 is to be able to compute the mean and standard deviation of a binomial random variable. So mean or expected value and standard deviation of a binomial variable or binomial random variable are given as follows. So a binomial experiment with n independent trials and probability of success p has a mean and standard deviation given by the following formulas. So mu of x is going to be n times p, and the standard deviation, sigma x, is going to be the square root of n times p times 1 minus p. So if we look at this example, according to Experian Automotive, again, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and standard deviation number of car-owning households that will have 3 or more cars. So if we want to find the mean, all we do is we take n, which is our 400, and multiply by our probability, which is 0.35. So 400 times 0.35 is going to give you 140. And for the standard deviation, you start the same way, 400 times 0.35 times 1 minus 0.35, and then you take the square root of that, and you get 9.54 as your standard deviation. So if you're sampling 400 car-owning households, you're probably going to end up with about 140 that have 3 or more cars and a standard deviation of 9.54. Okay, now if you want to construct a binomial probability histogram, we can look at some of these examples here. We have a binomial probability histogram with n equals 8 and p equals 0.15. And this was just generated. I think this was done in Minitab, but you could do it in StatCrunch as well, which is built into your MyMathLab. Okay, so we have 8 observations, p equals 0.15. And if we look here, we have 8 observation again, but we have p equals 0.5. This one is more symmetric because our expected probability is going to be 0.5, which is half, 50-50. 0.85 is going to be skewed kind of the other direction from the original, but still n equals 8. Now let's construct a binomial probability histogram with n equals 25 and p equals 0.8 and comment on the shape of that. So if you look at this, we have n equals 25, p equals 0.8, but what you actually notice is that this is much more normal looking than the original because we have more observations. And then if we look at n equals 50, you'll see that it is even more normal than the original because of the number of observations. And then we have n equals 70, again, looks even better. So for a fixed probability of success p, as the number of trials n in a binomial experiment increases, the probability distribution of the random variable x becomes bell-shaped. Okay, so you could see that through the demonstration just a second ago. You can see that it does become bell-shaped as we have more and more observations. So as a general rule of thumb, if n times p times 1 minus p is at least 10, then the probability distribution is going to be bell-shaped. So this is a rule that you'll kind of have to verify as you're doing some of your problems. So let's use the empirical rule to identify unusual observations in a binomial experiment. So the empirical rule states that in a bell-shaped distribution, about 95% of the observations should be within 2 standard deviations of the mean. So what that means is that 95% of the observations lie between mu minus 2 sigma and mu plus 2 sigma. So any observation that lies outside of this interval is going to be considered unusual because the observation occurs less than 5% of the time. So if we look at this example here, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. A researcher believes this percentage is higher than what is reported. So he conducts a simple random sample of 400 car-owning households and finds that 162 cars had 3 or more cars, or 162 houses had 3 or more cars, and we want to know if this is unusual. We had already calculated the mean. We just took our 400 times our probability, and we expected to get around 140. Now this researcher got 162, which does appear to be a little higher than we would expect, but we want to know if it's unusual. So if we look at the standard deviation that we had calculated, it was 9.54, and we obtained that by taking our 400 times our probability of success times 1 minus our probability of success, and then taking the square root. So we get 9.54 for that. And then if we actually put this together, mu minus 2 sigma is going to be found by taking our 140 minus 2 times the standard deviation, and we get 120.9. Mu plus 2 sigma is going to be found by taking our 140 plus 2 times our 9.54, and we get 159.1. So this result is unusual because 162 is larger than our 159.1, which is our 2 standard deviations. So this is a fairly unusual result if the actual true proportion of households was 35%.